Welcome to Multi-Objective Optimization with Stella. My name is Kareem Chichakly, and I'm happy to give you this tour of this new feature that we have in Stella to complement the stuff we did last time on single objective optimization. So there's a lot of stuff I need to talk about before we get going, just so that you understand some basic stuff, because multi-objective optimization is fairly complicated. Optimization period is complicated. There are two major types of optimizers. The first time is a local optimizer, which will quickly converge to what's called a local optimum. If you look at this picture over on the right, you'll see there are three peaks. So each of those are optimas. And if you're maximizing, if you're minimizing, there are two blue peaks that are also optimas. And a local optimizer could converge to any of these. The global optimum would be this tall one in red at the top. So a local optimizer will always find the optimum when there's just one. But when there are many, it can find a different one, which is not really the optimum. So we do support this in Stella. We have Powell. It's a hill climber. It's very efficient. It's very fast. Works great. But you have to be careful. It may not find the global optimum. There are also global optimizers that, by their name, try to find the global optimum. We have two types of those in Stella. The first one is an exhaustive type, where it does an exhaustive search, and that's called grid. And the problem with grid is it will become very slow as your problem gets larger or you want higher resolution. And it's only as good as what the resolution is. It does literally a grid search. It would look along, if you look at the grid lines in this picture, it would look along those grid lines pretty much. And then we have an evolutionary method called Differential Evolution, which is designed specifically to find the global optimum without an exhaustive search. So we say quickly find, but it's slower, of course, than Powell, which is a local optimizer. There are also two types of optimization problems. The first is single objective. So we solve for the one best value of the fitness that we need. So you get one answer, for example, 17. And then there's multi-objective, where you can solve for either. So the problem is multi-objective, but you could either solve for the single value of the fitness, which also gives you one answer, say 17. And you do that by creating what's called either composite fitness, which I'll explain on the next slide what these are, or using some lexicographic technique, and it uses a single objective optimizer to do it. Or you use a true multi-objective optimizer that will give you the non-dominated front, which is our set of best solutions along this line. Over on the right here, I have two objectives, and these show the trade-offs between these objectives. As I move up here from the left to the right, objective 1 goes down while objective 2 goes down while objective 1 goes up. So there are trade-offs there, and we can pick what's best for our situation. The definition of the non-dominated front is that every solution on here is better than the others in at least one objective. That's it, just one objective. And you need a multi-objective optimizer such as differential evolution. So the different ways to look at multiple objectives, the first is using what's called the composite fitness. And again, we use a single objective optimizer to do this. We assign weights to each objective based on their importance. So for example, if we're looking at reducing sediment load and what cost it would be to do that coming out of a river, we can weight the sediment load, we can weight at 70%. We think it's worth that much versus 30% for the cost. So it's more important to us in that case. And you can easily do that in Stella. In the payoffs, you can assign weights and do this quickly. The other approach to do it, to try to reduce a multi-objective problem to a single objective, is what's called a lexicographic approach. And actually, you could reduce a 4-dimensional problem to a 3-dimensional or 2-dimensional doing the same thing. And what we do here is we optimize the most important objective first, and then using the set of solutions that come from that are really good solutions, we then optimize the second most important objective, and so on. And so in this example, we would get a set of solutions where we optimize the pollution load, and then we try to optimize costs subject to those solutions, and then we get a final solution. So in both of these cases, we're getting just one solution, versus in true multi-objective, we optimize all of the objectives at the same time, and we get a trade-off curve that gives us the full set of solutions that meet our conditions, and we get to pick which solution along here that we would like. And you'll notice along here, whenever we have a curve, we have diminishing returns past a certain point. Right here in the middle, we call this the knee. And past this, we have diminishing returns in both directions. For example, as we increase cost going to the left, pollutant load is not going down very much. So we're spending a lot more to reduce cost. And as we go to the right, as we reduce, as we increase pollutant load, it's costing us less, but it's minor, right? So there's diminishing returns in both sides. The other thing I need to define before we start so you can understand what differential evolution is doing is the concept of exploration versus exploitation. So global optimizers need to explore the solution space, and by that, I mean we're looking everywhere in this. We're looking at all different places on here, exploring the nooks and crannies to make sure nothing's hiding. So that's exploration. At some point, it needs to switch to what's called exploitation so that it can converge to the global optimum. If it just explores forever, it won't converge. In exploitation, we take our best solutions and we push them to be better and better and better, and that's called exploiting. How much we need to explore before we exploit is specific to your problem, and you'll see there are several things that help you decide that, and you can obviously experiment with them. If you exploit too early, you'll get what's called premature convergence, and you'll end up, say, at a local optimum right here instead of at the global. And if you set something so you explore too long, you may never converge, but it will certainly delay it in any case. So with that behind us, let's talk about what differential evolution is. First of all, it's an evolutionary method from the name, which means we have a population of solutions that we evolve over time, and that time is we have what we call several generations. The next generation is based on improving the solutions from the previous generation. It can be either single objective or multi-objective, and in Stella we support both of those. And how it works is it combines a solution that we already have with the weighted difference of some other solutions. So say, for example, I have two parameters here and I have a solution. Here's my solution, R0 it's called, and we'll call it the base vector in DE, that's what they call it. And then we'll take two other solutions and we'll take the difference between them and multiply them times F, which is our scale factor. And this is typically between 0 and 1, but it can be up to 2. And it tells us how far I want to move from my base vector, actually, because what we're going to do next is we're going to take this difference multiplied by the scale factor, and we're going to add it to the base vector. And that will give us not our child for this generation, but a mutant vector. We then need to do crossover to get the actual child. So that's how it works. And it automatically adapts from exploration to exploitation. And how fast it does that is controlled by both the variant of differential evolution you use, which we'll talk about on the next slide, and the value of F. So the larger the F, the more it will explore, and the smaller the F, the less it will explore. The other main parameters, because it's evolutionary, we need to be able to set the population size, that's how many solutions we have each generation, and the number of generations that we want to run. So that's a little background information. The variants in the algorithm, there are a few of them, and these are all supported in Stella. The first is RAND, and I recommend you use that if you don't know anything else. RAND favors exploration over exploitation. It randomly chooses all of the vectors that it uses. On the other extreme, we have what's called BEST, and BEST favors exploitation instead. And it always uses as the base vector that it adds these differences to, it always uses the best solution so far. So you can see it's exploiting. Whatever that best one is, I'm going to vary it, and I'm going to move around that. So it's favoring exploitation. There are also two intermediate ones, target to RAND, which is a compromise that leans toward exploration, and target to BEST, which is a compromise that leads toward exploitation. Why would you choose one of these? Again, I would start with RAND. If you're not converging properly, you might try BEST or one of the other ones. If BEST converges too fast, you try one of the intermediate ones. That's how you would do it. And there is one more fallback option. Oh, before we do that, let me show you. Powell is over here on the exploitation side, way over, a lot farther probably than BEST is even on this scale. There's one other method. If you find that you think there's a spot in your search space that's being missed consistently, and you want to look at that, you want to test that, you think the global maximum is somewhere else than where it's finding, then there's something called either or that's specifically designed to try to find gaps that are in the search space. So if you run into that problem where you think it's not actually finding it and you've tried other things, either or will help you find that. As I said, once we have the mutant, which we get from the mutant vector, which we get from one of these previous algorithms, we then apply crossover. And that tells us how much replaces the parent. So the child is initialized to the parent, and it takes some values from the mutant vector. And how many it takes is dependent on the crossover probability and method. The target, the parent, is actually not the same as the base vector. It's a different vector, and we won't go into that in detail. But it's basically the nth vector. If I'm creating the nth child, it's the nth vector, the nth solution in the population. So the crossover probability goes between 0 and 1. When it's low, it's favoring exploitation. When it's high, it's favoring exploration. So you have a lot of parameters here that are messing with how much we exploit and how much we explore. Crossover is never 0. Even when we set it to 0, at least one thing will cross over. There are two types of crossover. The first is binomial. It's normally called, in the evolutionary algorithm world, it's normally called uniform crossover. But what it does is it does a binomial trial. That just means it picks a random number. And if we're below the probability, it copies the value over. Otherwise, it doesn't. So in this case, we have, say it's like 0.2, which is the default. We end up with 2 values coming over. We might have had 1 come over. We might have had 3 with a value of 0.2, depends. But on average, it's going to be 0.2 of them, 20%. And the other type is exponential. An exponential replaces a consecutive set of values in the solution. And the idea here is you use this if you think that groups are related, and we're going to swap out those groups instead of swapping out individual ones, individual genes, they're called. We think if groups are related, we'll swap out entire groups. And this is actually a combination of 1-point and 2-point crossover in normal evolutionary algorithms. Finally, if a number goes out of bounds, and we do specify bounds for all our parameters. So if a value goes out of bounds, we have what's called, there are several ways to redo this, but the way we do it is we use what's called DE bounce back. And bounce back, what it does is if I have a limit for that parameter, and I'm here at the base vector or whatever, the base vector, and I'm mutating over to here, if it's outside the bounds, I reinitialize it inside this range between the base and the limit, and I get a value here. The other common method would be just totally reinitializing it, but in this case, we favor staying near the base vector, which is chosen for a reason. So we use bounce back always. There are some limitations to differential evolution, in fact, for all evolutionary methods. The first one is called the no free lunch theorem. And it says that over all possible search spaces, all methods for finding the optimum will perform equally well, and that includes random guessing. And what this means is that only the exhaustive search can guarantee that you're going to find a global optimum. So you're using DE, you may still miss it. And as I said, if you suspect that, you can try the either or variant and see if it finds it. Convergence is also a limitation to an evolutionary algorithm. So DE converges fairly quickly to near the global optimum, but it doesn't. Then you have to run a little while longer to actually get exactly there if you want to. It's very slow to pinpoint an exact value. When I say slow, I'm saying relative to, say, Powell. Powell just, bang, goes right to it. And with multiple objectives, you have another problem with these algorithms that use non-dominance. So it's not really DE, they will end up dancing around it. So you may think it's still changing, and so it hasn't converged, but it's as far as it's going to go. It won't move any farther forward. It will just move slightly around where it already is. So if you are interested in a single objective problem, you can use, and you have multiple optima, you could use DE to get near it and then use Powell to finish that, to get to the exact. And we'll demonstrate that right now with a very simple example. So we're going to maximize x times y, where x goes between 0 and 20. And I hope you can see that the answer had better be up in this corner, which is 20 times 20. There's only one optimum here, which is 400. So let's go look at that. You can ignore most of this. I just have this fitness is set to x times y, which is what we said we're looking at. And if we go over to this tab here, if you missed the first one, we have this model analysis tools tab here. And under here, you normally start in sensitivity. You have to set your payoffs. My payoff I set to fitness by just adding it here, and I called it obj for objective. And I'm on the optimization tab, it defaults to Powell, which is what we're going to use, by the way, to start. And you say which thing I want to, what payoff I want to look at. In this case, I want to look at my fitness value, which is obj. So these are default parameters we don't have to mess with, and we have to set up our optimization parameters. In this case, we have x going from 0 to 20 and y going from 0 to 20 also. I'm not showing you the mechanics of that. We went over that in depth in the last one. But basically, I just hit the plus sign, and I pick the variable. They're both on here already, and I say what the range will be. Okay? So I can run that either by clicking run here, or I can hit O run over here, which is what I more typically do. And when I do that, it says it ran 26 times, and the best value is 400 with x at 20 and y at 20. That's awesome, right? It found the answer pretty quickly. That's what we want. Okay, great. Let's try DE. So we're going to go over here. We're going to change from Powell to differential evolution. We have to select the payoff. In this case, it's objective. And we want to maximize it. We have to pick the action. The action is maximize or minimize. There's some other things that we'll talk about when we get there. And the default is rand. You can see the other options are here that I talked about: best, target to rand, target to best, either or. We're going to just use rand. Crossover type, you should use binomial unless you know you need exponential. So binomial is the default. Number of generations, 10 is fine. I'm going to use a small population size of 5. That means I'm still going to run 50 runs compared to 26 on the Powell. And if I want it to stop sooner because it's within a certain tolerance, I can set that, but I won't. The scaling factor by default is in the middle. That's F. It's 0.6 is pretty good value to start from. 0.2 is a crossover probability, is also pretty good value to start from. I don't need this because these are specifically for these other two methods, target to best and target to rand and either or. I can use it. I can set any seed. And here I've set, again, the parameters haven't changed. They both go from 0 to 20. So let's run this and see what happens. If we run it, we've just run 50 runs, and it only got to 319 or 320, and that's at 16 and 20. It's going to change. If I run it again, it might end up at 399. Okay, it's random. So I may need to run it a lot longer. So at this point, if I know that's not the optimum, so why would I do this? I know there are multiple optima, and I want to get near the global. So if I'm near the global already, I can just go back. It remembers my best solution. It actually changed my variables. Stella does, changes my variables to my last best solution when I'm in single objective mode only. And I can go back to Powell and I can finish the optimization from here. Now, it still took Powell 23 runs to get to the 400 from where we left off, which was at 320. So it still took it a little while. We didn't save a lot there, but the point isn't to save anything. The point is if I have multiple optima and I want just one answer and I want to make sure I'm near the global, I can use DE to get near there, and then I can just switch to Powell to go the rest, because Powell picks up from where you left off. DE does not. It's always initialized randomly. Okay? So that's a handy technique to know about. So we just went through all those. Again, let me emphasize that this will only work for a single objective problem. If it's multi-objective, you're out of luck. You have to use DE. So let's look at a simple multi-objective problem. And this problem, by the way, you will find on our blog at blog.icesystems.com. So we have a new product entering the market, and we want to capture our market share as early as possible at our lowest expense. So we want to minimize advertising expense and the time to achieve market share. If we look at that model very quickly, there we go. It's just a Bass diffusion model, and we want to minimize how much we're spending on advertising, but we want to get as many adopters as fast as we can in case someone else comes in the market. So we're going to use adopters at time 3 to be a proxy for market share, but we want to minimize both. We don't actually have to do that anymore, but it was easier before 162 to minimize both. I would use its reflection, potential adopters as its reflection. And we'll do that in a second. So let's go back here. And if we look at the optimization, we have 2 payoffs. The first payoff is potential adopters, and I specified that to be at time 3, not at the end. It doesn't make a big difference, actually, but it's still a pretty big value at time 3. And my second one is cost, which is just advertising expenditure, which is something I sum over here. Here's my budget, and I sum it up, and that's what I have. And I look at the final value of that. The optimization itself is set up to optimize both the non-adopters, the potential adopters, and the cost. So those 2 payoffs that I just looked at. We're using differential evolution. All these are default parameters, rand and bin. Population size 20 was default, but can be whatever you want. But I changed the number of generations to 30 for this because it needs to run a little longer. And I have 2 parameters that I change. So my budget is initially, let's go back to this, is initially $10 million per year. But I allow myself to decrease that by some rate, some fraction per time, per year, I believe it's set up to be, and what time I start decreasing that budget. And the reason I do that, by the way, let's just run the model very quickly, not looking at this. If you look at my adoption from advertising versus adoption from word of mouth, adoption from advertising is very high and important to get this whole thing started at the beginning, but then it's dwarfed by adoption from word of mouth. So do I still need to keep paying $10 million a year all the way out here? Probably not. So I'm going to try to optimize that, see what my spend would be. And I already set it up, so we can just run it. I'll run. So at the end of our run, we ran 30 generations. It found 20 solutions. It doesn't have to find 20 non-dominated solutions from a population of 20. And those look like this. Here we go. There's our front. That's our non-dominated front. The knee is somewhere around here, this purple or red. And we can click this button up here, the S button, to see what all of these solutions are. Let's say we're trying to find the value around what when we have expenditure of 12.5, I want to know how many adopters there are. By the way, this is adopters at the end. And remember, we actually optimize for adopters at time 3. So these numbers won't be the same numbers we see in the S, which will show us the values we had. So this tells me all of my values in this front, all 20 values. It doesn't tell me where it is. In 162, I can say include output variables, and now my objectives show up here as well. And I can see where I am. I'm trying to find around 12.5 for advertising expense. I can scroll down. There it is right there. We can see we decrease at a rate over an entire year. I drop it, but starting at time 0.75. So after 3/4 of a year, I drop my expense over the next year pretty quickly. And this gives me, actually, this is the final value on this graph. If I want the earlier values, I think I can go back here to 3. I don't know. I haven't actually tried that to see if it does that. Yeah, it does. Great. So my 12.5 is still here. And so I had 534,000 potential adopters left. So about half at that point for that price. The problem is when I go back here, this value was at the end. So I'm kind of I've kind of lost that value if I'm looking at that. But anyway, there's a first optimization. Pretty simple, very straightforward. But let's go back and, oops, not to that one. Let's go back to this one. And instead, let's change. What we really want to know is the time. How long does it take us to win? In this case, I'm looking at half the potential population. I want to minimize that. So I can go back here. I can go back here to the optimization, and I can change my payoff. I set up a different payoff. There's a third payoff here. Market dominance time. It's just the time to win half my customers. And that's a very simple calculation, by the way. If adopters is less than half of my population, then I set it to 1. Otherwise, then I throw 1 in here. So that's the flow. And so I accumulate the flow while adopters are growing, and I stop accumulating it once they reach half. So time to win half, the stock will hold that value. And we did just run it, so I should be able to just show you that at a certain point it stops changing. So it changes up to the point where we reached half, and then it holds the value where we were. So great, everything's wonderful there. And let's go back to the optimization. We're going to use that instead of the number of non-adopters. And we're going to minimize both of those. Oops, that's maximize. So we need to go to the pop-up and change that to minimize. Okay. And these are the same, and we'll run it with these same values. The decrease rate goes from 0 to 1. The start time is anywhere from 0 to 4 when I start decreasing it. And let's run that again to see what the results are. So this time we ended up getting only 10 solutions out of 20. And one of the reasons is, well, let's just look at this for a second. What I didn't show you, and I meant to, so let's very quickly go back to the setup. Decreased start time it doesn't make any sense to be anything but a multiple of dt. So I have it incrementing by dt. So this goes from 0 to 4 by dt. There are no other values, and my dt is in fact 0.0625. I got 10 values here instead of 20 because this discreteness of time, because I'm switching between dt, there are multiple values that are going to end up at different dt's. They're all going to get wiped out. I'm only going to pick the best value for any given start time. And so I end up with fewer values. So you have to be careful. If you're using something like time that's related to dt, you're going to run into restrictions like it has to be a multiple of dt. And as soon as it becomes discrete, the number of solutions you get is going to be fewer, and you may want more. Maybe this isn't enough solutions. So what can I do? One thing I can do is I can have dt again. I wouldn't do this too much, though. You have to be careful. When you change dt, it's very important that you not go crazy and set it just to any random value, but we can get away with having it. And in this case, we also have to change our parameter to use half of it, the new value of dt, or we're not going to do any better. If we run it again with this smaller value of dt, we get 18 solutions out of 20 that are non-dominated, and we have more choices here that we can pick from. So that was just to show you that you have to be careful when you're using dt. Something that's related to time. Okay, in another example, let's say we actually don't exist in a world where there's no competition, and we have another competitor that comes in, and we're going to first look at the case of another competitor entering at the same time as we do, and we want to maximize how many customers that we gain, our market share, and minimize our advertising costs. So we're going to maximize one and minimize the other. And we'll then look at a case where the rival enters later. Does that change things? So if we look at that model, which is over at the end, of course, this is the same model. We have batch diffusion here, and it's just reflected up here for a rival. So we have one set of potential customers get divided between the both of us. We're starting exactly the same time. All of our parameters are identical. So you would expect we would both capture half of the market no matter what we do. And here I let you change when the rival actually starts advertising, when they actually enter the market. If we go back to the optimization of this, we want to, we have two payoffs. We have the number of customers that we get ourselves, which is right here, and we have our cost, which is here. So no, our total cost, which is in this stock here. But it's based on our budget, what we're spending here. We're not looking at theirs. We don't care. So we're looking at both of those. We want to maximize adopters. Again, we can pick maximize or minimize through this pop-up. That's only available in 1.6.2. Before 1.6.2, there was a minimize option down here that applied to everything. You either maximized or minimized everything. But 1.6.2 is out, and you can use this. It's a really powerful feature. So I can maximize adopters. Otherwise, all my other settings are the same. I haven't changed anything. 30 generations, population is 20. A decrease rate is still 0 to 1. Start time is still 0 to 4. And I should use DT by DT because otherwise the values are pretty meaningless that I get back if I care about the actual values. I mean, this doesn't make any difference. The software is going to force it to the nearest DT. But when I get my answers, they will be just random numbers when, in fact, it used that increment. So it helps me just for the answer for it to match. So if I run this now, where I'm trying to minimize my cost and maximize my adopters, I did get 20 non-dominated solutions. And you'll see we have a different shape of our non-dominated front here. And that different shape is due to the fact that we're maximizing one of them instead of minimizing both, which would bring them here. If we maximize both, the shape would be over here somewhere instead. In any case, you'll see we have serious diminishing returns on our advertising expenditure after a certain point. We're not gaining a lot of customers for spending all this extra money. So we have all these solutions, but we could pick something. We still get only half the customers, but we can look here and we can see by including output variables. We can try to find, the knees down here somewhere, but let's try to find this blue point, which is around 30 million. So 30 million of advertising expenditure. There's 33. That might be it. That's it. Okay. So we spend 33 million and we pretty much get half the customers by doing that. So we probably don't want to spend 105 million when we could spend 33 to get half of them. So we have serious diminishing returns after a certain point as far as spending more money. We could do the same thing. We said, what if they start 6 months earlier? What if they come in 6 months earlier? So rival enters the market. This is in years. So 6 months later would be 0.5. So what if they enter half a month after we do? How does that change the picture? Well, for one, we should be able to get more than half the customers because we started earlier. So let's just do that and see what happens. I didn't change anything else. We have 20 non-dominated solutions, so that's good. Notice we ended up with almost 700,000 customers. We're like 675 or something. And after like this magenta point or this gray point, we're really not getting much back for our money. The knee is right in here, this green or magenta point. We might pick this gray point, which is again around 30 million. So again, to find that, it's a little over 30 million. So 31.62. So if we spend about 32 million, we end up with 672.5 thousand customers. Actually, it's probably million. And if we spend a lot more, we can spend all the way up to 105 million. But if we spend twice that, we gain what? 3,000 more, because that's the one right next to it. So this helps you make decisions like that and make trade-offs. That's the reason why you typically would do multi-objective optimization. There was a question about constraint handling last time, and I want to talk about that because we added some features in 1.6.2 because for multi-objective optimization, it actually makes a difference what you do here. Make that a little bigger. So this is the model we're going to use for our first example. Let's go back. So it doesn't work well with multiple objectives. With one objective, a penalty function works pretty well. So instead, we use what's called constraint adaptation with differential evolution. And what that does is the same thing. If both solutions are feasible, if they're within their constraints, then it just does what it normally does. one solution dominates the other. If it Pareto dominates the other, it's the same. In other words, it's better in all objectives. An infeasible solution dominates another infeasible solution only if its constraints are Pareto dominate the other ones' constraints. So we're applying the same non-dominance idea to the feasible solutions for the actual solution values and to the objective function values for that. And for infeasibles, we're applying it to the constraints instead. And of course, a feasible solution will always dominate an infeasible one. And why is this important to keep these solutions around in multiple objective problems? Is because otherwise you end up throwing out a ton of things that help you find, that help you explore the corners of the search space. So, and you don't want to do that. All of your constraints need to be written as less than or equal to 0 or less than 0, which is a common thing in evolutionary algorithms. So in Stella, to use this, you first have to rewrite your constraint as less than or equal to 0 or less than 0. So for example, if I have x is less than or equal to 10, I subtract 10 from both sides, and I have x minus 10 is less than or equal to 0. So I need a converter that calculates x minus 10. That will be my constraint. I put this in a converter, and then I tell Stella that it's a less than or equal to versus a less than. If it's greater than, well, I multiply both sides by minus 1, which makes it minus x minus y is less than or equal to minus 100, and then I add 100 to both sides, and I get 100 minus x minus y, and that would go into a converter as my constraint, and I would tell Stella that's a less than or equal to also. Could be a less than, but in this case I chose less than or equal to in both cases. Here we use our notation we use in our equations, although you won't be entering less than or equal to. You'll just be entering the constraint value here. And constraints are always minimized. You don't have any choice on that. You obviously wouldn't want to maximize your constraint. So let's look at a very simple problem again with the same problem, but we're going to have a constraint. A constraint is that the multiplication, the value of that value, the product cannot be greater than 100, okay? It can be 100, and that gives us actually a number of solutions along this line. There isn't one solution anymore. There are multiple solutions. And I'm going to make it a little more complicated. I'm going to, just so we don't just find anything, I'm going to make it a little harder. I'm going to say x is incremented by 0.3 and y is incremented by 0.4. And we'll look at it using a penalty function, both a small penalty and a larger penalty function. So here we have, whoops, that was not the one. Why did it not go back to it? This one. So on this one, I have set up a penalty function, and the penalty function is 10 times the constraint, but right now I'm going to use 1 times the constraint, which is small penalty. So basically I'm subtracting. My constraint is fitness minus 100, has to be less than or equal to 0. I'm making my fitness worse by, if this constraint is negative, I don't care, so that's why I have a max of 0. If my constraint is positive, that means I violated the constraint. I'm going to subtract that from my fitness, so my fitness is worse. That's how a penalty works. And then in my optimization, I will optimize the penalty instead of the actual objective. If I do that, so great, look at this. After 10 generations, it found a payoff of 100. My fitness is 100. At x equals 11.4 and y equals 18.8. I hope everyone who's listening to this knows that that does not multiply. Actually, my payoff was 100 right here. The penalized fitness. I hope everyone realizes that's not 100. In fact, my fitness value is well over 100, and I violated my constraints. Let's see if I can get it to hover and tell us the product is 214 instead of 100. My fitness was 100. Isn't that great? So I need to actually be careful about how I do penalties. And if I want this to work, I need to I have to make the penalty very large for going out of bounds. And in this time, I'm going to make it 10 times larger. I'm going to run it again, and it will work in this case. So my payoff is at 99.84 at 19.2 and 5.2. So 99.84 is here. My fitness is also that. It's less than. Great. Everybody's happy. So I can use penalties, but I now have in 162, I can also use constraints. Same problem. I can set my constraint to be this. And the way I do that let me show the one that's already set up to do that so I don't have to change anything. So my constraint is still fitness minus 100, but in my optimization, so I have my payoff and I have my constraint. So this is my constraint. So I have both of those as payoffs, and in the optimization, I choose DE. I can maximize objective, but I can also say I'm going to use a limits, but I'm not going to minimize or maximize it. I'm telling it it's a constraint. My choices here, I can maximize it. That means it's an objective. I can minimize it. That means it's an objective. I can keep it less than or equal to 0. That means it's a constraint. Or I can keep it less than 0. That means it's a constraint. So here I have the limit that I get to set, and it will now optimize this with, by the way, I set X to go by 0.3 and Y to go by 0.4, but I did that before. I just didn't show you. That's just the last parameter here. I'm still running 10 generations of 20, which I did for this problem originally, but I have this added constraint. And if I run it now, very quickly, after 10 generations, the best payoff was 97.9 at these two values. By the way, I can run it again. Oh, this time I got 99. I got a better value. Remember, there are many possible values. I got even a better value, almost 100 at 15.6 times 6 times 6.4. So if it runs fast, it doesn't hurt to run a couple of times, or you can actually run more generations. That's the other. If I ran it for more generations, or I had a larger population size, but let's say I'll run it for 20 generations instead, my payoff is 99.96. I run it again, it's 99.84. It's more likely to have the value close to the closest to the actual optimum the more generations I run it. Okay? So I have one other example I do want to show you before we quit. So let me show you. That was a single objective problem with constraints. I'm going to use a simple multi-objective problem with multiple constraints. It's not time-based, I'm sorry. I come up with a time-based problem that has multiple constraints. I didn't have one in my back pocket. But I did have this multiple constraint problem that's multi-objective. I'm trying to minimize the cost of this beam. I'm trying to weld this beam on here. It has to support 6,000 pounds at the end of it, and I want to minimize the cost of this beam, and I also want to minimize the deflection at the end. I don't want this to bend a lot. I have 4 parameters that are shown here, which are the width of that beam and the height of that beam, and I have the length of the weld and the height of the weld are constraints. Notice that the total length of the beam is determined. This has to be 14 inches out, so it's determined by 14 plus the length of the weld. Okay? So those are the parameters, but I also have several constraints on this problem. The shear stress has to be less than about 14,000 pounds per square inch. The bending stress has to be less than 30,000 pounds per square inch. The buckling load has to be greater than or equal to, 6,000 pounds. It can't buckle with, we need to hold the 6,000 pounds without buckling. This width minus this has to be greater than or equal to 0. In other words, this width has to be greater than or equal to this height. So the height of this weld, the weld is also the width of the weld. It's a circle. So it's the same. So the weld cannot be wider than the beam. That's what this last constraint is. If we look at that one, which is now at the end, so this is really not very interesting. This is a bunch of math. I have my parameters here. I have my objectives over here. I have constraints in different places. Constraint here, constraint here, constraint here. There's a constraint at the bottom. Great, whatever. What I really care about is how I set this up, which is why I'm showing it to you. So I have several payoffs. They all have weights of 1, final value. So my cost, I have the deflection. I have so cost and deflection are the things I want to minimize. I have my 4 constraints here. They're all 1 final value. That's all I care about because it doesn't change. This is not time dependent. My optimization is DE again. I set up cost and deflection both to minimize using this pop-up. And then I set up all 4 of my constraints. The yield limit, the weld thickness limit, and the buckling limit all keep less than or equal to 0. So those are all constraints, and it knows they're all constraints. I'm using RAND by default, binomial crossover scaling factor F of 0.6, crossover probability of 0.2. I actually did set a seed so I could reproduce the results, but you don't have to. And I chose a population size of 100 for 1,000 generations. That seems like a lot, right? We're going to be here forever. And we also have several parameters that were defined in this problem. So how thick the beam can be, how wide it can be, the weld length, etc. So those are just set how they're set. And if I run this, wow, it's taking forever. Oh, we're halfway done. Oh, it's done. So we had a population of 100, and we found 100 non-dominated solutions after that, which is great. They're all non-dominated after 1,000 generations. You know, honestly, I would be really surprised if they weren't after 1,000 generations. After 10, no. But after 1,000, they better all be non-dominated. And then we get this cost versus deflection curve. These are all our solutions. Oh, by the way, I didn't tell you how I set this up, this graph. I probably should briefly tell you that. It's a comparative graph, and it's a scatter graph. So it's a comparative scatter graph, but the important thing is I have to check this option, show single point per run. If I don't even think it shows me the values. Yeah, so anyway, I need to set that value. That's how I get one of these fronts at the end. In any case, here is my, like this dragging over here doesn't help me a lot except to show me they're bunched up over here, but somewhere here in my knee is somewhere in here. I probably want to pick a point where my deflection is low. So down here is low, and my cost hasn't gotten crazy high yet. So I might want to pick a point here where the cost is 10 or a little higher. And again, I can press the S button. These are all my parameters for all 100 values there. But I want to find the one that has a cost around 10. So I'm going to show include output variables. And I'm going to go down here, and I'm going to try to find something around 10. So here's 13. Maybe there's something closer. Here's just under 13. As I remember, here's 10, pretty much 10 right here. So 10, I have a cost of 10 and a deflection of very, very little. And this tells me what parameters I need to get those. So what the thickness of my beam needs to be, what the width needs to be, what the weld needs to be, both its thickness and its length. Okay? So in summary, differential evolution is very powerful when you have multiple optima. And also when you want to use multiple objectives, when you want to have a trade-off curve so you know. And I showed all these were 2 objective. You can do 3 objective. You can do 4 objective. But remember, as you increase the number of objectives, it becomes the number of generations you need to run it for becomes, quote, combinatorially explosive, which means you need to run a bazillion generations by the time you get to like 4D. So you probably don't want to run more than 3 objectives. I do have a 3 objective example, but we don't have time to show it. In that case, I use the scatter plot to show 2 each against each other. But you could also take it out somewhere else and do a 3D plot of it. Okay, you want to be careful of premature convergence. If you don't have enough generations, you don't have a large population size, you may end up converging early and you don't realize that. Also, if you don't have the right method, if you favored exploitation tremendously, you may converge early on a local optimum, so be careful. And you also want to be careful of late convergence where you're just too cautious and just runs forever. But more importantly, about late convergence, you just want to realize that if I go back to this right here, this curve is not the same as 1 generation ago. Things will bounce just a slight amount from here. It wouldn't have changed. So you could have said it converged at 900, for example, after 900 generations, and the answer may be close enough. So you need to be careful of running it too much. And that just gets back to the issue that once I converge, once I'm actually as far as I can go, pretty much, the algorithm is just going to move a little bit. It's just going to jitter around that front, and you're not going to really gain anything by running it more. Remember that there's no guarantee that you'll reach the global optimum. And if you decide to use penalty functions, for example, you want to use Powell, which doesn't support constraint handling. It doesn't need to. You can use a penalty function. Just be really careful. And make sure that that constraint, how you add in that constraint, is strong enough that you actually get a real solution that meets the constraint. If you use a penalty function for multi-objective for DE, then you'll limit your exploration. You're automatically cutting off a whole ton of your exploration on all sides if you do that. So it's not a good plan. And now that we support constraint handling in DE, you don't need to do that. So now I'll open the floor for questions. There are a number of questions already out. Before I do that, I'll just very quickly tell you we have some upcoming webinars. They're not scheduled yet, but we're going to look at causal tracing. We're going to look at sensitivity, and we'll look at calibration. That will probably be in the summer, late summer, in data handling. Okay, so questions. Let me just see what they are. Okay, so someone says in our first model where I did the BAS diffusion, they say there's no rival or competitor that's explicit, but there's some group of competitors. They're asking specifically. If not, they think the market share would be 100% from the beginning. So that's not true. You're right. If you're an existing business that's already there, then you probably have 100% market share if you don't have any competitors. But the point is, if I'm entering a new market that doesn't exist before, there's a potential market size that we already know of, let's just pick a number, 10,000 people. None of them have your product yet, so you have zero market share. And as you sell your products into that potential market, if I sell 5,000 into that market of 10,000, I only have 50% of the market because the market is 10,000 people, and I haven't reached them all yet. So you have to grow to that market share even without competitors. So that's an important point. That's a good question. So for maximum value, I'm not quite sure. I'm going to go back and look at one of these things and see if we're talking about the maximum value not on the graph, on the optimization. So if we're picking min and max on here, for example, on the parameters, those have to be constants. Those cannot be equations. Sorry about that. Those have to be real numbers. They aren't calculated. Can we use other optimizers such as linear and nonlinear optimizers? So the optimizers that are supported in Stella today are Powell, which is a hill climber, Grid, which is a exhaustive search, Stepper, which you shouldn't use. It's just there to play with if you want to. We'll just ignore that. And differential evolution. So those are your choices. You can use any of those and nothing else. Are there more formal ways of finding the knee point? So the knee is basically where your diminishing returns start in any direction. So it's very subjective. I don't know of any formal way. You can find the exact middle of the knee. By the way, you can find, okay, this is the exact middle between here and here. I can find that. I can calculate it. It looks like it's around here, but I can actually calculate that. And then it's going to be, the knee region would be on either side of that, an equal distance, and you decide how far you think it should be before you have diminishing returns. The point of giving a trade-off curve is actually finding the optimum can be very subjective based on political factors, social factors, etc. And you want to have trade-offs to be able to pick what the best solution is, what the most palatable solution for the most people are, whereas an optimizer that's looking for one objective will give you one, and that's it. How does differential evolution relate to optimal control theory or linearization? Wow. Yeah, I'm going to say it doesn't. If you know it does, then please tell me how, but I don't know how it does. Can you please explain when I can use the plenty of constraints? In which situations would you use the penalty? So I'm going to tell you that it's better to use the constraint handling over the penalty always. So if you're not using Powell, I would use the constraint handling always. If you're using Powell, you have no choice. You have to use the penalty function. Do I have an example of multi-objective optimization on an ecosystem model? In fact, I have a paper on that. But we'll try to email out a reference so that you can see that. But there are many cases in the literature on that. Are there other methods for handling constraints? Yes, for example, penalty functions. This is a very common method that's used in evolutionary algorithms, even though it's called constraint-adapted differential evolution. You can find it, and it has a name in DE specifically. You can find it in other evolutionary methods. People have adopted the same idea. So that's probably those are probably the two major ways to handle constraints. Okay, is there a rate for quitting, exiting, drop of customers in the model? No. Simple model does not have people dropping out. We can use a more complicated model that does do that. We also don't have customer switching. If you go to the blog, I have examples that do all of these things. But there is nothing here. We don't lose customers. Customers don't drop using our product and go back. We don't have, in the other model, we don't have people switching between different brands either. For constraint greater than, I gave an example of that. So I'll just go back to that very quickly. You basically go back, you have to do the math to make it a less than or equal to. So this example was greater than or equal to. You multiply both sides by -1 to make it less than or equal to, and get a 0 on this side, which is how I get this on the side. So you have to convert it to less than or equal to or less than. How can we apply this to potential solutions for global warming or the nuclear threat? So that's a much broader question than I can answer in this question in this session. But again, if you look at one of the papers I did on applying this to an environmental problem, I did in fact look at how you can use optimization to help you find better solutions that help you be more resilient to climate change. So, but that's a very big question. How would you deal with uncertainty in the optimization in the BAS diffusion model? So you know that how they interfere with the optimization results. So I do not have uncertainty built into this model. To do that, you would have to do sensitivity analysis with optimization, or optimization with sensitivity analysis, I guess it is. And we covered that last time in the last webinar. We showed how to turn on sensitivity analysis when you're doing an optimization. And that's, let's see, here it is. So you set up a sensitivity and where you think the uncertain parameters are and what the ranges are, and then you include that sensitivity analysis as part of the optimization. So there's a question about this particular equation. That's not a minus sign. That is a bullet. So it's positive x plus y. It's not minus x. Yeah, it's kind of unfortunate that at this level the bullet's a minus sign, but that's the bullet symbol. That's not a minus sign. Just so you aren't confused. Good point. Can you have the references? Yes, I will send you some references with this. And let's see. In our help, there's one of them, but I can send you the additional references. So at this point, there are no more questions, and thank you for joining us. And I hope you can see us. We can see you again in one of our future webinars.